Hi and welcome to this video where we're going to look at fats, oils and soap. This is the last of the videos that relate to the level 3 content. We will put some up, I will have some up in the next wee while looking at some common exam questions, but this is the last video that's focused on new content and concepts. So fats, oils and soaps seems like an interesting combination to put together, but they're really key. So fats and oils are basically a type of ester. They're a triester that is formed between long-chain fatty acids. So fatty acids are basically carboxylic acids with a minimum of about 10 carbon atoms, usually 12 to 18 carbon atoms. And so that provides your carboxylic acid part. And then you have glycerol, which is a 1,2,3-propan-triol. So it's 3 carbons and 3 alcohol groups. The difference between a fat and an oil is simply that the fatty acids in fats are mostly saturated, so the carbon chains contain mostly single bonds, whereas oils tend to have more unsaturated fatty acids, so there will be double bonds within that chain. What does this really look like? However, if you can picture, here we have 2 molecules, well, 4 molecules kind of. On the left hand side is glycerol. Okay, so that's the big 3 carbons, 3 OHs, and some other H's. There should be an H on the top and the bottom as well. And we have 3 fatty acids. So you can see the carboxylic acid group, and that long zigzag represents the carbon chain. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18 carbons, stearic acid. And there are 3 copies of that fatty acid. These form esters. So where that you take out those 3 waters and you make some new bonds, and we have fatty acids, fats. This is a fat or an oil. So you can see now the ester groups are formed, again, between the double bond O of that fatty acid and the O of the alcohol. And this is showing 3 different fatty acids bonded to our propan-triol, the glycerol. The top one is a saturated fatty acid, so that's all single bonds. The middle one is a monounsaturated fatty acid, so it's got 1 double bond. And the bottom one is a polyunsaturated fatty acid. A couple of things to note with this. First thing is that all of the double bonds have a cis configuration. Okay, they are all cis isomers. And all naturally occurring fatty acids are cis double bonds. If you manipulate your fats, then sometimes you get trans fats formed. So that's where your double bonds now have a trans configuration around that double bond. Okay, that's just a little aside. More importantly, the other 2 things to note are that here you have 1 fat molecule, if you will, and the 3 fatty acid chains are 3 different chains, and that's quite common. It's not required that all 3 fatty acids are the same. The other thing you might be able to see is that where you have all single bonds, the chains line up quite nicely, so they pack together quite well. But as soon as you start throwing double bonds into the mix, and especially depending on the positioning of the double bond, then actually you end up with the molecules not being able to pack down so well. That becomes quite important because when we talk about fats and oils, fats tend to contain large amounts of saturated fatty acids. And because they have large amounts of saturated fatty acids, they pack together quite well, so they have stronger intermolecular forces. This means they have higher melting and boiling points. So fats tend to be solid at room temperature, whereas oils tend to contain more unsaturated fatty acids, and they don't pack together as well, which means they have weaker intermolecular forces, which means they tend to be liquids at room temperature. So the two terms fats and oils can be used interchangeably, but fats typically come from animal sources, and they typically have lots of saturated fatty acids, and they tend to be solids at room temperature. Oils tend to come from plant sources. They contain lots of unsaturated fatty acids, and they tend to be liquids at room temperature. The exception to that rule is coconut oil, and you can look that one up for yourself if you're interested to find out more about that. Okay, so you might have been intrigued at the title of this video, Fats, Oils and Soap. How does soap fit into this? Well, soap is formed through the base hydrolysis of fats and oils. So when you take a fat or an oil, so a triglyceride, and you hydrolyze it under basic conditions, so that's with sodium hydroxide or potassium hydroxide, then you get two products, or multiple products, I suppose. So you get glycerol, which is fine. You don't need to worry about the glycerol. And you get the carboxylate anions of the three fatty acids that are present. And this is what historically has been known as soap. Okay, so if you ever read historical novels or anything set in the past, they might talk about making soap and mixing up your tallow or your animal fat or oil with lye or caustic or something like that. So that's your hydroxide, and heating it, and it breaks it down. And these molecules that form these long chain fatty acids with a carboxylate anion on one end are really quite intriguing little molecules. So if you can picture it first, let's have a look here. So we have at the top our triglyceride, and when we react it, we get our glycerol, and we get three carboxylate, long chain carboxylate salts. So you've got, in this case, a 16 carbon chain with a double bond to O, an O minus and an Na plus. So it's got an ionic end and a long alkyl chain, effectively. The alkyl chain is non-polar, right? So it likes to dissolve in non-polar things. But the anion end, or the ionic end, is, well, ionic, and ions like to dissolve in water. So you've got one part of the molecule that wants to dissolve in non-polar substances, such as fats and oils, which are non-polar. That's why fat and water don't mix, or oil and water don't mix. And at the other end, you've got an ionic substance, which does want to be dissolved in water. So these two ends of the molecule are sometimes described as a hydrophilic end, an end that likes water, and a hydrophobic end, a side that doesn't like water. Now that helps it work as a soap, because what you get is one end of the molecule, the hydrophobic end, the bit that doesn't like water, that wants to be mixed in with oils. And you've got at the other end, you've got the bit that wants to be into the water. So what it ends up doing is being able to dissolve fat molecules or grease molecules or dirt molecules and dissolve them into water, which they wouldn't normally do. Does it by forming these things that are called micelles. So the yellow blob in the middle is basically your fat, grease, oil, dirt molecule. Or blob, not really a molecule, it's more like a particle. And these green blobs with the kind of wiggly tails are your carboxylate chains. So you've got the carboxylate group at the end, that's the hydrophilic head, and that's dissolved in water, which is the blue stuff around the outside. And then you've got this yellow tail, which is your alkyl chain, and that part wants to dissolve in the fat molecule. So you end up with the fat molecule being encapsulated by this the soap molecule, or these soap particles, these alkyl chains with hydrophobic heads, hydrophilic heads, and it dissolves up that fat molecule or that fat particle. And so that's kind of how soap works. So the base hydrolysis of a fat or oil is sometimes known as saponification because it makes soap. And that is where we're going to finish up today. So I hope you found this useful and valuable, and I hope to see you back soon for the videos on how to answer exam questions. Okay, see you then, bye.